In the intellectual landscape of 1960s theoretical physics, a peculiar and frustrating situation had developed. The world's powerful new particle accelerators were producing a veritable battery of strongly interacting particles, or hadrons, with bewildering variety. This proliferation, often called the particle zoo, defied simple categorization and presented a profound challenge to the very idea of elementarity. Physicists found themselves with a wealth of experimental data and a deficit of coherent explanation. Two powerful yet seemingly incompatible theoretical frameworks vied for dominance. One approach, the quark model proposed by Murray Gell-Mann and George Zweig, offered an elegant organizing principle. It postulated that all hadrons were composite particles, built from a small set of fundamental constituents called quarks. This model possessed immense classificatory power, beautifully arranging mesons and baryons into neat symmetry groups. It treated hadrons as collections of point-like objects. A competing and philosophically distinct program was the analytics matrix theory, championed by Geoffrey Chew. This bootstrap philosophy viewed the very idea of fundamental constituents with suspicion. It proposed that the spectrum of hadrons arose from a web of self-consistency conditions imposed on the scattering matrix, or smatrix, which connects initial and final states in a scattering process. In this view, every hadron was a composite of all other hadrons, a democratic principle with no elementary particles at all. The theory focused on global properties like analyticity and unitarity, deriving its predictive power from the behavior of scattering amplitudes at high energies. This behavior was elegantly described by Rake theory, which organized particles into families lying on trajectories where their spin was a linear function of their mass squared. These two views presented a deep schism. One described particles as built from fundamental quarks, the other viewed them as emergent states in a dynamic interplay of forces. The stage for a synthesis was unexpectedly set in 1968 by the Italian theorist Gabriele Veneziano. He discovered a remarkably simple and yet powerful formula for a 2-to-2 scattering amplitude. Using Wheeler's beta function, which can be expressed as the product of gamma functions, he wrote down an expression that possessed an extraordinary property. It simultaneously described the exchange of an infinite tower of resonant particles in one scattering channel, a feature of low-energy physics, and exhibited the smooth, continuous behavior predicted by Rake theory at high energies. This was the birth of what became known as duality. The amplitude showed that the sum over an infinite number of resonances in the S channel, representing the collision process, was equivalent to the exchange of particles in the T channel, representing the forces. One description was all that was needed, the other was automatically included. Veneziano's formula was a mathematical revelation, but it lacked a clear physical interpretation. It was a beautiful answer to a question that was yet to be fully articulated. It was here that Yoichiro Nambu provided the crucial insight. In a lecture delivered at a symposium at Wayne State University in 1968, and later in a more formal publication, Nambu offered a profound physical picture for the mathematical miracle of the Veneziano amplitude. He proposed that the duality observed in the formula was the signature of a new kind of fundamental entity. A hadron, Nambu suggested, was a one-dimensional extended object, like an elastic string. For meson, the string would have a quark at one end and an antiquark at the other. The observed particle state, the resonances organized along Rake trajectories, corresponded to the different vibrational and rotational modes of this string. The energy of the hadron was stored in the string tension, providing a natural explanation for the relationship between mass and this model, in its elegant simplicity, provided a powerful mechanical explanation for duality. Consider the scattering of two such strings. The interaction could be pictured as two strings coming in, merging into a single, excited intermediate string, which then breaks apart into two final strings. This corresponds to the S-channel description, with its tower of intermediate resonant states. However, the same interaction diagram, a continuous surface traced out in spacetime known as the world sheet, could be viewed from a different perspective. It could be seen as the exchange of a piece of string between the two colliding hadrons. This corresponds to the T-channel description, which generates the force between them. The key insight was that these were merely two different ways of looking at the same underlying physical process. The dynamics of a single, continuous world sheet automatically contained both descriptions. Nama's string picture rendered the abstract duality of the Veneziano amplitude concrete and intuitive. The immediate consequence of Nambu's proposal was a conceptual revolution. It shifted the focus of fundamental physics from point particles, a paradigm that had dominated since antiquity, to extended objects with internal structure. The model explained why only certain combinations of quarks were observed in nature. They were the endpoints of the string. It also provided a mechanism for quark confinement, as pulling the quarks apart would simply stretch the string, increasing its energy until it became more favorable to create a new quark-antiquark pair from the vacuum, splitting the string into two new hadrons. Free quarks were therefore an impossibility within this framework. Nambu's work gave physical substance to Veneziano's mathematics and gave dynamic life to Gell-Mann's quarks. It created a bridge between the matrix and quark model camps, suggesting they were describing different aspects of the same underlying reality. This breathtaking conceptual leap, from mathematical curiosity to a dynamic theory of strings, laid the essential groundwork for a radical new direction in theoretical physics. The full implications of viewing fundamental particles as vibrations of a string would unfold over the subsequent decades, leading physics into territories Nambu himself could scarcely have imagined. The conceptual leap initiated by Yoichiro Nambu in 1968, transforming a mathematical formula into a physical string, sent reverberations throughout theoretical physics. While Nambu provided the core physical intuition, he was soon joined by others climbing the same intellectual peak from different directions. Leonard Susskind at Stanford and Holger Bech-Nielsen at the Niels Bohr Institute in Copenhagen independently developed a similar picture of hadrons as vibrating, one-dimensional extended objects. This convergence of ideas lent immense credibility to the string concept. Together, their work culminated in what became known as the Nambu go-to action, a beautifully simple and elegant formulation describing the dynamics of a relativistic string. The action itself is proportional to the area of the two-dimensional surface, or worldsheet, that the string sweeps out as it moves through spacetime. Its profound achievement was in providing a fully Lorentz invariant description of a string's motion, thereby establishing a legitimate theoretical foundation for this new physical entity. However, this early version of string theory, now called bosonic string theory, soon encountered significant theoretical challenges. For the theory to be mathematically consistent and free of quantum anomalies, it required a spacetime of 26 dimensions. This was a perplexing result, a numerological demand that seemed disconnected from the four-dimensional reality of experimental observation. Furthermore, the theory's spectrum of vibrations included a particle with an imaginary mass, a tachyon, signaling a fundamental instability in the vacuum. It also described only bosons, particles with integer spin, failing to account for the fermions like quarks and electrons that constitute matter. These difficulties, combined with the spectacular success of an alternative approach, caused the string model of hadrons to fall from favor. The rival theory that captured the community's attention was quantum cryodynamics, or QCD, formulated in the early 1970s by physicists including Murray Gell-Mann, Harold Fritsch, and Heinrich Leutwiler. QCD presented a more conventional quantum field theory of the strong interaction. It described quarks as fundamental point particles possessing a new type of charge, called color, and interacting via the exchange of massless gauge bosons, the gluons. QCD provided a natural explanation for quark confinement. The force between quarks, mediated by gluons, strengthens with distance, making it energetically impossible to isolate a single quark. For a time, Nambu string seemed relegated to the status of a clever but ultimately approximate description of the complex flux tubes that bind quarks together within the QCD framework. The fundamental theory appeared to be one of point, particles and fields. The story of the string, however, was far from over. In a remarkable intellectual pivot, John Schwarz and Joel Scherk revisited the perceived flaws of bosonic string theory in 1974. They focused on a specific massless particle with a spin of 2 that consistently appeared in the string's vibrational spectrum. This particle had been a source of embarrassment for a theory of the strong force. Schwarz and Scherk made the audacious proposal that this unwanted particle was, in fact, the graviton, a hypothetical quantum carrier of the gravitational force. With this reinterpretation, string theory transformed overnight. It shed its identity as a theory of hadrons and emerged as a candidate for a theory of quantum gravity, a potential theory of everything that could unify all fundamental forces. Nambu's original duality, an observed property of hadron scattering, now hinted at a deep principle governing the unification of gravity with the other forces of nature. This conceptual rebirth triggered the first superstring revolution of the 1980s. The development of superstring theories, incorporating a symmetry between bosons and fermions called supersymmetry, resolved the tachyon problem and reduced the required number of spacetime dimensions to a more manageable 10. The work of Michael Green and John Schwarz demonstrated that certain superstring theories were free from the quantum anomalies that had plagued other attempts to unify gravity and quantum mechanics. The intellectual lineage traces directly back to Nambu's 1968 insight. His idea of duality, the equivalence between different physical processes, blossomed into a central organizing principle of modern physics. It evolved into the powerful concepts of T-duality and S-duality, which reveal surprising equivalences between string theories in different spacetime geometries or with different interaction strengths. This reached its zenith with the holographic principle and the ad-SCFD correspondence, which posits a duality between a theory of gravity in a higher dimensional the space and a quantum field theory on its boundary. The enduring legacy of Yoichiro Nambu's 1968 paper is therefore a testament to the power of physical intuition guided by mathematical symmetry. He perceived in the abstract patterns of scattering data the hum of a vibrating string, an idea that proved too profound to be confined to a single area of physics. That initial concept, born from the desire to understand the strong force, contained the seeds of a revolution in our understanding of gravity, spacetime, and the very nature of physical law. The principle of duality, which Nambu first articulated in this specific context, has become one of the most powerful and fertile tools in the arsenal of the theoretical physicist. It continues to guide the search for a final theory, revealing deep and unexpected connections between disparate corners of the physical world. Nambu's work serves as a permanent reminder that a single, elegant idea can change the way we see the universe.